Our next presentation is by Shannon Stott. Shannon is an assistant professor at the Department of Medicine at Harvard Medical School and assistant geneticist at the Massachusetts General Hospital Center for Cancer Research. Her background is in optics, microfluidics, and tissue engineering with a specific focus on how they are applied for clinical medicine and cell biology. The Stott Laboratory at Mass General Cancer Center has focused on developing microfluidic devices to isolate rate circulating tumor cells from the blood of cancer patients, as well as microfluidic technologies that can isolate tumor-specific extracellular vesicles from cancer patient plasma. Welcome, Shannon.
Well, thank you so much for having me here today. I really appreciate this opportunity to share my work. I'm the director of the Stott Laboratory at Mass General Hospital, and I'm excited to share with you the work that we're doing related to microfluidics and visual technologies with a focus on cancer. So I'm going to start by sharing a brief story about a recent haircut. My stylist asked what I did for a living, and when I shared I'm a cancer researcher, her response was, well, you aren't doing a very good job. Too many people are still dying. And she's right. And I think it's important that we continue to look at the numbers for where we're at with treating cancer. And if we look at the number of deaths every day in the United States from cancer, that number is still incredibly high, with 1,600 people dying every day in the US. And we take a look at this number globally, that number increases to 27,000 deaths per day. So this is something that we're working to see if we can improve the outcomes. And we look first at the initial diagnosis of cancer. So this is a visual of how the gold standard is done. A tissue section is abstained, and then a highly trained expert pores over this section under a microscope, trying to identify suspicious regions that might be the start of cancer. And so what we're doing with our work in multispectral imaging is adding a lot more life to these sections. So we're putting up to 21 different colors that are representing different proteins and markers inside these tissues to better understand and identify these early cancerous spots. And so this is an example of how we're using some image processing, identifying all sorts of different cell populations, but also the spatial architecture and interactions between these cells inside the tumor. We use machine learning, image segmentation, so that ultimately we have data points for over 1 million individual cells within every tumor section that we analyze. And so we're using this right now in head and neck cancer. And here's just an example of 10 different tumor specimens that were stained with our multispectral imaging approach. And so all of these patients were initially given the same prognosis as well as put on the same treatment. Yet when we take our eyes and look at this with the benefit of the multispectral imaging, you can start to pick up patterns or things that look distinctly different between these tumors. And what I know now is that for 3 of these 10 patients, they actually had far more aggressive tumors than what was initially diagnosed. And they would have benefited from having a much more aggressive treatment at the start. So that we're hoping that by bringing in our multispectral imaging that we can better diagnose these patients and get them on the right treatment. And we also recognize that this is a static snapshot of what's happening in that patient on that one day. And so my lab wants to push things further and understand how these cells in the tumors are interacting and communicating with each other in real time. And this is where we turn to microfluidics. So microfluidics is something my lab has over a decade of expertise in. And simply by pushing fluids through tiny spaces, we can have very precise control of anything that's inside that fluid. So here's an example of inertial focusing where we can position cells in very precise locations inside the device. And this is a high-speed video that we've slowed way down so that you can see how we can precisely package individual cells at a rate of 10,000 cells per second. And so what we want to do is we want to be able to capture that journey of a cell. If we only look at that last moment of what happens with the cell, everything starts to look the same. And so we want to use visual tech to capture these profiles and link them to molecular information so that we see this combination as a combination of optical barcoding with DNA barcoding. So to give you a little bit more detail about how our technology works, first we line up those cells with those fluidic forces so that we get this very exact pairing of 2 different cell types. But then we also package in a color code that allows us to track the droplet over time. We can then prepare these little mini bioreactors at a rate of 10,000 pairs per second. And here you can see a living cell that we can track what's happening there in addition to the color barcode that's surrounding it. So once we have our pairs created, we want to be able to watch them over time. Some of these interactions happen within just seconds and others take hours. So again, we turn to microfluidics to create order out of this disorder so that we can use things like computer vision to track these cells as they're interacting. And then once we have those cells all having those different specific interactions, we can then look at figuring out more about that interacting cell pair. And so we want to selectively sequence pairs of interest. Why we want to do that is because sequencing is expensive and we can't sequence cells at a rate of 10,000 cells per second. So we optically identify what is the cell or the droplet of interest. We apply an electrical pulse, and now we've actually been able to barcode just that one droplet so that we can selectively sequence those interacting pairs of interest. And so to conclude, when I think about the next 15 years and the impact of microfluidics and visual tech, I'm excited to see what those future salon conversations are going to look like. I think we'll be discussing about how so many more people are surviving with minimal treatment side effects. I'm hoping that we get 10 out of 10 patients put on the right treatment. We don't want to overtreat and we don't want to undertreat. But I'm also really excited to think about the impact, specifically in pediatric cancers. Microfluidics is wonderful with processing really small volumes, and I see so much potential for discovery there. I'd just like to thank all of you for your time. I'd love to connect with many of you, and I'd also like to thank my laboratory and funding resources.